So today I'm going to tell you a story about why adding redundant components to a system doesn't necessarily make the system safer. But first, there are a couple of things that I've got to make sure that I say. First one is, I completely made this story up. 100% invented this from whole cloth. I present it as a thing that actually happened, and it may well have happened. You know, something like it may have happened. Things like it certainly happen, but I don't know that this thing specifically happened historically in the context that I'm going to tell it, and I definitely can't point to any documentation or anything that this happened historically, even though I'm going to talk about it like it did. So, okay. Got it? Totally made up. 100%. Okay, cool. Also, that if you know anything about automobiles or about the history of automobiles, this story might make you itch a little. I apologize in advance. Please suspend your disbelief for a moment, if you would. So the story I tell goes that, very early in the history of automobiles, we were figuring out a lot of things that now to us today seem very sort of simple and common knowledge, but we hadn't figured them out then. And someone had to do that. Someone had to be the first. And in these very early days of automobiles, it was an all too common problem that the timing belts on their engines would break. So an engine has these valves. It's got these pistons and these valves, and then there's a crankshaft. And so the crankshaft is eventually attached to the wheels of your car, and the turning of the crankshaft is what makes your wheels go. That's very important. And the valves serve to let just a little bit of air in where it can react with the little bit of gasoline that's come in from the gas tank and makes a little explosion, and the force of that causes the crankshaft ultimately to turn. And it turns out to be very important that the opening and closing of the valves to let in air more or less quickly stay in sync with the turning of the crankshaft. Where if it gets out of sync with the turning of the crankshaft, the whole engine can be destroyed, sometimes catastrophically. And so in order to keep the valves opening and closing in sync with the turning of the crankshaft, there is a belt called a timing belt, whose sole purpose is to keep them operating as a single unit. If the belt connecting the crankshaft to the valves breaks, your engine's not going to go. And if it breaks the wrong way, your engine could not go because it went boom instead. So the engineer said to themselves, well, if the problem is that the timing belt keeps breaking, clearly we should put another belt on, so we have two timing belts connecting the valves to the crankshaft, so that when one of these belts breaks, the other one will still be there and will still be able to perform the operation, keeping the valves opening and closing. So this car manufacturer spec'd it out. They added a second timing belt to all of their new vehicles. They advertised it to their customers as, their new model of car was half as likely to fail catastrophically. And, people bought those cars. They, drove them away happy. And wouldn't you know, but not too long after, those cars started to come back with broken timing belts. Those cars started to come back with the same problem. And they were coming back after about the same amount of time and at the same rate. And so management came to this engineer and was like, okay, so you said that if we put a second timing belt on, that was going to, these cars were going to last longer and be more reliable, but they're still coming back at the same rate with the same problem. Why did you think that this was a good idea? Why did you think that this was going to work? And so the engineer says, look, it's just simple mathematics, right? We know that these cars last, 2,000 hours, let's say, and I'm just making these numbers up. These aren't real numbers, they're silly numbers, but just for sake of being able to do math in our heads, let's say we know that these cars last for 2,000 hours, and we know that, or we know that they should last for 2,000 hours. That's how long we want them to last. And also we know that most of these vehicles with only one timing belt are coming back to us. About 50% of them are coming back to us within the first 1,000 hours with a broken timing belt. And so that means that the mean time to failure of this timing belt is about 1,000 hours. And so clearly, if we add a second timing belt, then that will double the amount of time it takes for both of these timing belts to fail, right? Is that not how it's working? And that, management is like, no, that's not how it's working. We've got all of these cars, sitting over in the lot with 2 broken timing belts. Why are they both failing? So there are a lot of things that could potentially cause this particular pattern of failures. But fortunately for this car manufacturer, eventually a clever person working in their returns department noticed a pattern in when vehicles were being returned with 2 broken timing belts. The pattern that this person noticed was that returns with broken timing belts were much more common in the summer and in the winter than they were in fall and in spring. And so this got the research department of this car manufacturer looking at the timing belts and how they responded to changes in temperature. And what they eventually found out was that, so this was in the very early days of rubber vulcanization, and the material they were making these belts out of just simply wasn't all that good. In the spring and the fall, the material was kept at a, very reasonable temperature, very sort of moderate temperature, but in the summer, the belts would get very hot, and in the winter, the belts would get very cold, and it turned out that these changes in temperature had a big effect on the material property of the belts. It made them much more brittle than they were at other times of year, and so the belts basically lost their suppleness, and after enough cycles of, getting very cold, at night and getting warm during the day, or getting hot during the day, getting, cooling off at night, depending on the season, the belts got sufficiently brittle that at some point they would snap. So, and not only was, it these sort of temperature fluctuations that were making the belts, brittle and prone to breakage, but both belts were being exposed to the exact same temperature environment at the same time. And so both belts tended to fail at about the same time because they were both getting brittle at the same rate and were both under the same kinds of stresses that would eventually cause them to snap, generally speaking, when somebody turned the car on. And so when that happened, it was incredibly likely that, one belt would go and then the next belt would go right after that. Adding the second belt hadn't increased the reliability of the car at all. So it's easy to sort of look at a system and assume that these component failures, that we're seeing are sort of independent of one another. It's easy to look at, the timing belt snapping and say, okay, we don't really know why it's snapping, but it's probably kind of a random event, and we know that it happens at these particular intervals. We don't think that there are environmental factors, for instance, at play, and so we assume that we can add another component, we can add another timing belt, and the system will be more reliable because they won't both fail at the same time. This is also the idea behind RAID in hard drives, for example. And oddly enough, it turns out that heat is a leading cause of hard drive death. And if you have designed your RAID array around the assumption that only one drive at a time will fail and you'll have a long time to rebuild the array before the next drive fails, that is not a safe assumption. That is why a lot of people have moved from RAID 5, which assumes that one drive can fail and the array will still be safe, to RAID 6, which assumes that 2 drives can fail and the array will still be safe. And so I don't know how this car manufacturer solved this problem. Improved, material quality might have been a part of that. I know that they didn't continue to ship a duplicate timing belt because that was increasing the cost of the vehicle for not an increase in the reliability of the vehicle. But obviously they solved the problem because, timing belts don't break like this anymore. So one of the lessons to take from this story is just, simply that adding a redundant component doesn't necessarily improve the reliability of the system because both components are exposed to the same environment, sourced from the same manufacturers, under the same forces and stresses in the system. There's a lot of potential for what we call common mode failures. It's not simply that, in order to improve the reliability of a system, we can just double up all the components. Or if we could afford to double up all of the components, that would improve the reliability of the system. Unfortunately, that's just not the case. It's sort of a nice thing to believe, or it's at least a simple thing to believe, that we could have a much safer world if people were just not cheaping out on components. But that's not actually the case. So that's one thing to take away from this. The other thing to take away is that we've learned from studying the last 100 years of industrial accidents, the really bad ones, your Chernobyls and your Challenger disasters and, your 3 Mile Islands and all the rest. What we've learned is that most really bad accidents don't happen because of a component failure. Most of them don't happen because, a belt snaps or a bolt shears. But the really bad accidents, the ones that make the nightly news and the ones that hurt people a lot, almost always happen because two subsystems, both operating correctly according to their designer's intent, interact in a way that their designers didn't foresee, and that's where the accident happens. And that can be as simple as subsystem A is spec'd to output values in metric. Subsystem B is spec'd to take input in imperial units. Their designers don't realize that they're talking to each other, or they don't realize that, their systems are spec'd this way. The designers are just, going along, with the spec that they have in front of them, being like, oh, okay, got to send output in metric, oh, okay, got to take input in imperial. And as soon as they talk to each other, that's when a really bad accident can happen. And I wish that I was making that one up, but that's actually the Mars Climate Orbiter, which was a $125 million space probe that JPL funded, got launched was going to go to Mars, and it was lost because subsystem got a metric value and interpreted it in imperial and did the wrong thing, and that was the end of the spacecraft. And no number of sort of redundant, no number of duplicate sort of systems there. The problem wasn't that one of those systems failed, right? If you had a second copy of either of those or both of those subsystems, they would still do the same thing when they talked with each other. And so a lot of our work in software and in just, safety engineering in general is trying to find those places, trying to enumerate those places where systems can talk to each other, and making sure that we've sort of nailed down the interfaces. So there are a lot of techniques for trying to surface these specification errors, these places where interaction failures, or we call them, are possible. And we turn them up both while we're designing a system or while we're trying to add subsystems to an existing system, but also after accidents have happened, where looking at the system, trying to figure out which subsystems were involved in the accident and how they were interacting with each other, and where, potentially where those interactions broke down, can be a really powerful method of analysis. And if you're able to do this the way that a Boeing is, there's a book by Professor Nancy Leveson at MIT, which I will reference here because I reference it all the time, called Engineering a Safer World. I'll put a link up over here, probably, maybe over here, one of these places. There's an open access PDF on the MIT Press website. It's a great book. It's sort of the place that I learned a lot of what I know about how to think about system safety. And I can't recommend it enough. It's hard to use in software because it's designed for the Boeings of the world, where the 787, the Dreamliner, spent a decade in development. Each plane, each airframe has a 40-year operational lifetime, expected operational lifetime. And so, if their processes take 6 months to go analyze, the avionics subsystem or something that's fine. Where in software, we just move so much faster. If the code that I write today is in production and still in production in 2 years, whew, that's been out there for a long time, and maybe we should think about replacing that, right? We just operate at a very different tempo. And so the organizations that I've been a part of have struggled to apply the stamp family, the stamp techniques verbatim, but the philosophy and the worldview and the sort of research and understanding that motivates the stamp techniques is just incredibly powerful. It's, you know, everything that I've just told you is basically my attempt to summarize just a little piece of that. And so if you have any interest in this stuff, I strongly encourage you to check it out. It's really, there's so much more to it than what I've just given you. And, you know, my hope for this channel over the next few weeks, months, years, however long it lasts, is to bring more of this to you in a format that I hope will be, you know, meaningful and approachable, because like it's a thick book. And so it's not always the case, right, that adding redundancy is the wrong answer. You know, you look at semi-truck tires, for example, where they absolutely do have multiple tires on them, and it is the case that they don't tend to fail all at once. You know, one of those tires can blow, and the remaining tires will still support the load long enough for the truck to get where it's going. The lesson that I want to leave you with is not that redundancy is always bad, but that it's important to understand the idea of redundancy is just an easy thing to go to. We do that. It makes intuitive sense, but it turns out to just not work always. And so understanding that winds up saving, you know, time and money, aggravation, and sometimes, you know, people's lives and health. And so if we can do that, of course we've got to. Don't forget to like and subscribe, as always, if you want to see more of this. This is my first video on a safety topic, and there will be many more of these to come. So if you've liked this, please let the YouTube algorithm know and sign up to find out when I do the next ones. And thanks for watching. Till next time.